I want to expand what I've been talking about here a little bit. In one sense, I want to expand the idea of a case when we can consider an electrode reaction in somewhat of an empirical, semi-empirical way. And so let's take a simple case for electron transfer and see if we can derive the current that flows and the effective potential on that current flow. Let's think of a reaction that's only limited by mass transport. In other words, we have a molecule that is approaching the electrode from the bulk say molecule O, which is an oxidized molecule. And O might be something like iron 3+. That's an oxidized species. O might be equal to ferricyanide, a very traditional redox couple, part of redox couple. You might use more modern studies often use this compound rubipi, ruthenium tris-bipyridine complex. Not important that you know what it is, but just example of oxidized species. So the only barrier in this simple model of our system is going to be the mass transfer resistance. So the overpotential is eta mass transfer, or we can think about the rate of charge transfer is really limited by the rate of mass transfer. So that's the limiting case. All right. Now, let's see if we can draw a little diagram of our solution near the electrode surface. Suppose we have an electrode surface and we're going to think about extending out away from that electrode surface in the x direction. What's going to happen? Let's suppose we have two molecules in solution. One would be C sub r, or R, and the other would be O. And so C sub r is the concentration of R in solution. C sub O would be the concentration of O in solution. Now what about the concentration of species O in solution? Well, if we think about the concentration of species O in solution at time equal to 0, the species of O in solution is uniformly distributed throughout. In other words, before we do anything to the electrode surface by applying a potential to it or anything else, the species of O will be equilibrated throughout the solution to be the same. Let's suppose now that we apply enough potential to species O in solution to cause it to be reduced to species R. Now, if that's the case, we have to consider this concentration of species R in solution as well. And let's assume that species R concentration is also not equal to, is equal to 0. In other words, there's no species R in solution, but we do have species O in solution. And we're going to use the terminology C sub O star, where C sub O star is the bulk concentration. In other words, if we say I have 1 times 10 to the minus 3 molar solution of iron 3+ in solution, that would be the bulk concentration of this system. Whereas we're going to use C sub O as the variable concentration. That may be at the electrode surface, it might be some other point in solution. But in other words, C sub O star would be the bulk, C sub O would be the time-dependent concentration. All right, so I'm saying let's take our potential of our electrodes, let's step it to a negative potential, and cause an electrode reaction to occur, a Faradaic process to occur. What's going to happen? Well, species O, because it has to get to the electrode interface at some point, will be maintained at the bulk concentration at large distances away from the electrode surface. But as we approach the surface, the concentration of species O will start to decrease. And we'll say T is equal to T1. T1 is greater than T equals 0. So in other words, at some point after we've done this reaction. On the other hand, the concentration of species R, because it's being produced from species O, has to build up near the electrode surface. But far away from the electrode surface, that concentration is still 0. So outside the interfacial region, we've got the bulk concentration of our system being equal to what it was before we've done anything to the electrode surface. Right? R should be 0 out at long distances out in the bulk. And O will maintain its bulk concentration away from the electrode surface. But near the electrode surface, because we've perturbed the concentrations by applying and doing our electrode reaction, we get a change in the concentration profiles. Now, I've drawn these curves as illustrative of something, but not necessarily as something that's true. It just indicates that there will be a change in the concentrations near the electrode surface. What is that change in the concentration near the electrode surface? And that's really the important question we have to ask ourselves. Well, in order to answer that question, we can write down an equation for the term we call the flux. And the flux, usually abbreviated by capital J, is a term that has the units of moles per second per cubic centimeter, or per square centimeter. In other words, the flux refers to the amount of material moving through a particular area of spatial area in a period of time. So if we think about our electrode being say 1 square centimeter, we're thinking about material flowing through that interface and sort of in effect disappearing, but there's essentially a flux of material to that particular point. And we can also put in things like this, where we would say the flux at a particular potential, or a particular time and a particular place in solution would be equal to moles per second per square centimeter as well. So we can either refer to the flux, but we usually would refer to the flux at a particular point in the solution. Now, if you remember, I dropped this. Whoops, ouch. If you remember, our electrode reaction velocity also had units of moles per second per square centimeter. So V, the velocity of our electrode reaction, is the flux of electrons at the electrode surface. It also has to be true that it's the flux of chemical species at the electrode surface. In other words, those electrons have to be going somewhere. So if there's a flux of electrons, which we can measure by the current, those flux of electrons are doing a chemical process of electron transfer. Now we're going to consider two situations. One is where we have what I'll call very fast electron transfer, and this is really what I should say is very rapid or very large electron transfer rate constants. but they're very fast electron transfer. What's that mean? Well, that means that there is no real limitation on the overall reaction by any electron transfer event. As soon as that molecule gets to the electrode surface, it can undergo an electron transfer immediately. The barrier for that is very small compared to the other energetic processes that we're doing. So this actually turns out that that means that the rate of mass transfer is now going to be equal to the overall flux, or the rate of the reaction. So we've eliminated a couple things. We've eliminated the possibility of charge transfer, because we said it's a very simple, we've eliminated, the effect of chemical reaction, because we don't let chemical reaction occur in our simple model. And we've also eliminated this concentration polarization effect, the electron transfer effect in the system. So we've only remaining process to concern ourselves is this mass transfer rate. So if we can understand the mass transfer rate in our system, we can actually understand the relationship between current and voltage in our simple case. Now this kind of mass transfer process is often called Nernstian, or reversible. And we'll see why we call it Nernstian in a second. In other words, the reaction is very rapid electrochemically, and we're limited only by the rate of mass transport. Then we have a Nernstian reaction. The reason we call it Nernstian is that the systems, because the electron transfer is very rapid, that means that an equilibrium situation can be achieved very quickly in our chemical system. So we don't have to worry about whether or not things are in equilibrium, and that means that we can use the Nernst equation to derive the concentration of electrode species, concentration of species at the electrode surface. And we actually have to use the form of a Nernst equation that's only interested in the electrode surface. So in fact, what we're going to do is we're going to write the Nernst equation for a concentration of species O at the electrode surface, and the species of R at the electrode surface. Now before I used the Nernst equation, I used activities. Here I'm taking a little bit of a liberty, and I'm using concentrations. I've also changed the form of the Nernst equation that you've seen before by making it be at the electrode surface. Because that's all we're interested in, what's happening at the electrode surface, not in the bulk. And so we have the Nernst equation is going to set the concentrations of the ratios of those two concentrations. So whatever potential we apply to the electrode surface, we can use the Nernst equation to get the two species concentration ratios. And so just to remind you, concentration of O at the electrode surface at any time under these conditions would, with respect to the ratio of concentration of species R at the electrode surface at any particular time, is going to be equal to 1 at E0. And E0 is a special potential called the formal potential, and that's in fact where this is true. So kind of a circular definition a little bit. So in other words, if we're at E0, we're going to know that ratio is equal to 1, or when that ratio is equal to 1, we're at the E0 point. How are we doing on time? All right, a little bit more. Okay, I'm going to do a little bit of a derivation here, and we have to change the tape. All right. Okay, let's stop here then, and why don't we stop, take a break then, since we're going to change the tape, and we'll take a quick break, I think, and keep going.